All right, so if you haven't done the lab on page 17, do the lab, right? See how parallel circuits work with your eyes. I think that'll help you a lot with like kind of understanding like how this all these parallel rules come from. This is the analysis on page 18. I'm gonna go over it and hopefully try to make parallel circuits make sense, build some rules that we can use in our like circuits, right? So um, basically, a parallel circuit is when resistors, right? You have multiple resistors that are hooked up to the same potential difference. Now, that sounds complicated. You might be saying, "Oh, why? They're in lines, right? Isn't that what makes it a parallel circuit, right? Like the fact that they're parallel with one another." And yeah, this is true. Like they're parallel with one another. But the thing that makes these like for analysis questions, right? The thing that makes these like certain observations about their current and resistance and voltage, the thing that makes it true is the fact that they're connected to the same potential difference. Each of these resistors have wires leading straight back to nothing but the battery, right? So they're all hooked up to the same potential difference. That is what defines a parallel circuit. You will see parallel circuits that don't look parallel, and you got to identify that they are a parallel circuit so you can use these rules. That's just a definition though. Hooked up to the same potential difference, which in this case is the battery. So number 5 on page 18. Unlike in a series circuit, a parallel circuit, this current is not always blank. I would say not always the same or not always constant, right? So one observation you should have seen in your lab is that the current going through the 10 ohm resistor is going to be greater than the current going through the 25 ohm resistor, which is greater than the current going through the 47 ohm resistor. Right? You should have observed that, hey, each of these guys are getting different currents. Now, all of those currents, right? You can call it, like, I don't know, let's call it I1, this I2, and I3. Each of these currents are going to add up to the total current, like found right here, right? The total current going through the battery. They all add up, right? So total current in a parallel, so the next part is the total current in a parallel circuit is equal to the sum of the current in each individual resistor. Why does this make sense? Well, it's just junction rule, right? You have a certain amount of current coming through here. I'll call this I initial. At this junction, right, the current's going to split, right? And then whatever remaining current is going through here, this marker kind of sucks now, whatever current is going through here, it's going to split again. But by the time all the current passes through here, at this junction and eventually at this junction, by conservation of charge, all of your current is going to be returned back, right? If you think about I1, I2, I3, they all end up coming back to form the full current again. So that's why that's true. Write an equation that can express number 5, pretty simple. You could just say that I initial equals I1 plus I2 plus I3, and if you have more resistors, right, so on and so forth. Number 7, in a parallel circuit, the current is always largest in the branch with the smallest resistance, and the current is always smallest in the branch with the smallest resistance, or largest resistance. So for that blank, for number 7, it's largest and smallest. So what it's saying is, hey, what you should have found, and I'm going to explain it shortly, I just want to go through some of these questions. But by observation, you should have seen that, hey, this resistor is getting more current than this one, which is getting more current than the 47 ohm, right? So as the resistance increases, the individual current will get smaller. We're going to explain that, but for right now, that's just an observation, right? Hopefully, you saw that with your data. As you add resistors in a parallel circuit, the total current flowing in the circuit will increase. That's kind of strange, right? Adding resistors increases the current. That is unlike series, right? In a series circuit, if you had back-to-back resistors, adding more resistors is only going to increase the total resistance and decrease the current. But we kind of have the opposite going on with parallel circuits. This is an interesting observation. And you should have seen this, right? If I show you my data, you should have seen this with 2 resistors, the total current is 0.84, but when I add a third one, it's 0.97, right? So you should have seen that in your data, and I'm going to explain it I'm going to explain in a second. Let me pull back that page. We're just going off of observation here. This is kind of a key idea, and I kind of hinted on this earlier. The voltage across each resistor in a parallel circuit is the same, regardless of its resistance. You can think about this two ways. Both ways are like equally valid. For the mathematical people, this is just a loop rule consequence, right? Loop rule states that for any loop of wire, the sum of the voltage, right, the potential difference for that loop equals 0. So, right, if I think about, okay, for this first loop, right, you can make a loop with like any loop of wire. For this first loop, if this is 12 volts, right, a 12 volt battery, doesn't matter what really, this marker kind of sucks, that kind of sucks. And I'll keep it, but I want to use the blue one. If this is 12 volts, for this loop, this resistor better take away 12 volts, right? 12 minus 12 has to equal 0. Same thing with this loop, right? With the battery in the second branch. Better take up negative 12. Same for the third. This is a consequence of the loop rule. Another way you can think about it, the way I like, because this is more like I think the loop rule kind of explains how do you know they're the same. This kind of explains why. A positive charge right here, oh, this is a bad one. A positive charge right at the top, like right at the battery, it's going to have a certain potential, right? The battery, like as the positives go through, it's going to gain like 12 volts or whatever. So you have a certain amount of potential. Like all the charges, right? Because this is current, we got a bunch of these charges. As they flow down here, no matter which junction, like no matter which path they go, they still have the same potential, right? They still have that same like 12 volts or whatever. That's why there's 12 volts going through here, right? Doesn't matter what path they take, whatever potential they started here, they gotta remain the same going through these things. So we can kind of deduce that, right? We can kind of, not deduce, but I think that's a fairly good explanation as to why they have the same voltage. So the total voltage in the parallel circuit is equal to just the voltage across like each resistor for number 10, sorry. When you add the inverses of the resistances together, does that equal the inverse of the total resistance? Yes. This is an equation, and I might make I could make like a quick like derivation of this equation if you're curious on where actually I'll do it real quick. So here's the resistance equation, right? So I know that this better be true, right? The currents better equal to the same thing. Sorry, what am I saying? I know the sum of the individual currents going through each thing is going to add up to the total. So what I can do is I can kind of say I initial, so I should do this. I can kind of say, I know from Ohm's law, V equals IR. No, sorry. Yeah, V equals IR, so I is equal to V over R. So I can say, okay, this I initial is going to be equal to V over R1 plus V over R2 plus V over R3, okay? So what I'm doing is I'm just saying, okay, the voltage across current 1, or resistor 1, right, over R1 has to equal current 1. V over R2 has to equal current 2, right? V over R3 has to equal current 3. And now what I can do, what I just hopefully explained and hopefully makes sense, is that the voltage across each resistor is the same. I can factor out this V. I can say V is equal to 1, well, this whole thing is equal to V times R1 plus 1 over R2 plus 1 over R3, right? So I get this is equal to I initial. Now what I can do, if I divide both sides by V, right, these V's drop, and I get I initial over V is equal to 1 over, like the inverses, right? The sum of the reciprocals of each resistor. Well, what's I initial over V? That's, right, if you think about Ohm's law, right, if I divide both sides by V, up here I get I over V is equal to 1 over R, right? If you think about the slope of like current versus voltage, 1 over R. So this is 1 over R total. This is the parallel equivalent, like total resistance equation. So if you add up the reciprocals of each of their resistances, it'll equal the inverse of the total resistance. And if that's kind of flying over your head, we'll do practice problems with this equation, but that's just what the equation is. And you can see in your data when you were like writing down the inverses of each resistance, it should have added up to the inverse of the total. Does the equation from number 11 work in all cases? I don't know if they meant in all cases of parallel circuits or in all cases of circuits. This really only works for like branches, right? If you have a parallel branch, right, you can find that the equivalent resistor for these three using this equation. Doesn't work for series, stuff like that. All right, list at least one way currents differ from series and parallel. In the series, the current is constant. In a parallel, it's not, right? It splits up. List one way the voltages differ between series and parallel. In a parallel, the voltages are the same, right, across each resistor. Not true in a series, right? The voltage kind of divides up for each resistor. You can think of it like that, right? Each resistor has a different voltage used up. List at least one way the resistances differ from each type of circuit. When I add resistors to here, this equation shows, right, if you think about the inverse. Yeah. This equation shows that whenever I add elements, the inverse gets bigger. When I take the reciprocal of that, the total decreases, if you're a math person. But the main point is, when I add resistors in parallel, the total resistance decreases, while in a series, if I add resistors in series, the total resistance increases, right? So that's kind of the main point here with parallel circuits. Hopefully this kind of cleared up some things about parallel circuits if you were kind of confused with the analysis. And yeah, thank you for watching. Hopefully this video wasn't